Hello, my name is Jose Andrew Guevara, and this will be my EE320L final project, a digital to analog converter. So, just for background, the digital to analog converter, or a DAC for short, is a device that takes digital data and converts it into analog signals. These analog signals are often connected to an amplifier in order to play the converted values out loud. Thus, the carrying and conversion of digital audio is the primary selling point of these DACs. DACs are also found in television and mobile phones in order to convert digital data into analog video signals. So DACs are very common in everyone's daily routines, whether they're seen or heard. And for our digital to analog uh, converter circuit, the main component will be the operational amplifier. The op amp is a device that amplifies given input voltages, and they can be used for numerous mathematical operations such as summation, integration, differentiation, and they're often connected to external feedback components such as resistors and capacitors. So in the pictures we have here, we have a FIO A3 amplifier and a Korg DS DAC 100M. And here we just have a simple um, schematic outline of how a DAC would work in terms of inputs and outputs. So we would put in 8 bits of digital input, and what will come out is just one analog voltage. So in the bottom here, we have the LM741 op amp by Texas Instruments. We have the simple schematic here, and we have the pinouts right here. So going into our digital to analog converter circuits, uh, each voltage source we have here acts as a binary bits where 15 volts is a logical 1 and a 0 volt is a logical 0. So the most significant bit will be the top voltage source and the least significant bit will be the bottom voltage source. The effect of each bit in the circuit is twice the value of the previous bit, which mimics bit values in binary, with the most significant bit being closest to the inverting inputs, which would be right here. The value will be naturally the highest. So previously I did do this converter with minimal resistor values and minimal voltage values in order to have a 0 to -1 volt range, and I decided to change it so it would be more close to how a binary bit would act. So because we changed it to um, 6K resistors, 3K resistors, 9.6K for the feedback resistor, and 15 volt voltage sources, we will be receiving a output voltage range of 0 to -15 volts. So again, 0 to -15 would match the 4-bit values that we could possibly receive in binary and in our voltage source. So continuing on, the numerous 6K and 3K resistors were placed in order to lower the amount of input coming from the lower voltage sources. Thus, the least significant bit only changes the output voltage by -1 volts when the bit is set. So as you can see, this bit is set, and the output voltage will only come out to be -1 volts, whereas um, the recurring voltage sources, as previously mentioned, will be double of what this would be. So turning this one on would be -2 volts, -4 volts right here, -4 volts right here, and -8 volts right here. But I'll show you the output voltage later on. So next we would have the bit values as previously mentioned. So here I just turned on one by one just to show what the output voltage as previously shown would be. So like I said earlier, -8 volts. Bit 3 would be -4 volts, bit 2 would be -2 volts, and bit 1 would be -1 volts. Because they're so similar to, um, or because they nearly mimic the values of decimal and binary, or binary bit values, we will be using a decimal and binary table to decipher or to see where um, each bit would affect the output voltage. So um, the expected outcome of our digital to analog converter would be a would be an analog signal, of course. So uh, 1 second. So as you can see from this expected outcome, feeding in incremented values for our voltage sources will result in a staircase-like output voltage. So as we change and increment the voltage sources, we will be receiving high and low values of like this, and it's just going to continuously change from zero, or it's going to continuously range from 0 to negative 15 volts. Um, because I made the values proportional to a binary bit, we can see it's nearly exact as the 0 to negative 15 range. And that will be it for my final projects. So now I'll just be showing you my testing proof. Here's the actual circuits, just to show it will run. Here I have the binary value 1101, which should be 13 in the binary table. So running this, we will obviously receive a negative 13 volts. And just to change it up, we subtract, or we make that, we clear that. So that would be 1001 for our expected voltage output, which would be negative 9 volts if I'm correct. Negative 9, nearly negative 9 volts. And going back into it, problems encountered. Primarily the only problems I encountered for this circuit would be figuring out exactly how much to how many ohms to put in each resistor. So I continuously adjusted it in order to find the right range to get -1, or to get a range of 0 to -1 volts, which was my initial attempt before. And once I was able to find the perfect feedback resistor and resistor values for these, I essentially just multiplied all of them by 15 just to be able to get a 0 to negative 15 range instead. And think and the only reference I was able to use um, just for op amp inspiration and circuit setup inspiration was the EE320 Lab 2, which would just be on operational amplification or amplifiers, apologies. Um, so yeah, that will be my final project. Thank you very much for teaching during the pandemic. We really appreciate it, and have a great summer. Thanks.